Okay, can you hear me now out there? Yes, yes. It's a pleasure because Sally has come here to give this talk, but also to be one of our invited people to interact with people here. And some people who are invited interact a little bit with people here. But Sally is interacting very vigorously with people here, and people are appreciating this. She's booked up until she leaves, but I'm sure that if people want to talk to her as a result of this talk, she'll be only too pleased to see them, because she's that kind of person. She has, well, I'll summarize very briefly. Her first degree was in physics and Latin, if I'm not mistaken, and that's, for someone who comes to talk in Spain, is very significant, because Latin is disappearing from the curricula in everywhere, in particular in Spain, and it's particularly interesting to see that that was an interest, an academic interest of yours. It's not usual for a scientist, and particularly positive, if I may say so. And then she's worked, I won't go into more details, but she's worked in massive stars and their interaction with the surrounding media, and in both. So she is both a stars person and a gas person. And that, again, is not completely usual. She's worked with Rob Kennicott, who was a thesis supervisor and is well known to everybody, I think, and also with Phil Massey, who is perhaps not quite so well known in Europe, but is one of the leading people working in massive stars. Among her many occupations, one of the most recent is that she's been elected to the Council of Aura, which runs, among other things, Kitt Peak and other national observatories. She has worked in the Lowell Observatory in Flagstaff, and she's now in the University of Michigan. So, well, she told me not to go further and further. There are many, many things I could say, but I won't say them because we're waiting to hear her talk. So I'll hand you over, please.
Thank you so much, John. It's been a wonderful visit here, and it's really great to be here. So thank you so much for your invitation. I really appreciate this. So today I'll be discussing a topic that's of wide astrophysical interest, and I've titled my talk, The Fate of Ionizing Radiation from Massive Stars. And most massive stars are in star-forming galaxies. I'm going to feature some work that I've been doing with my research group, and we have a name for my research group. I had my students think of a name. It is FANG, Feedback Activity in Nearby Galaxies. Where is my thing? This is work done with my former postdoc, Eric Pellegrini, who's now at the University of Toledo in Ohio, not in Spain, and my current graduate students, Jordan Zastro and Ann Jascott. So this is a topic that, as I mentioned, affects a large range of topics in astronomy, and it can be boiled down kind of to a very simple question, which is, are H2 regions optically thin? And we care about this for a number of reasons. In the first instance, because if we don't understand the radiation transfer of the Lyman continuum, then we may have some problems when we try to use these H2 region diagnostics. And of course, we use them in a great variety of environments, all the way from very locally here, the Orion Nebula and other H2 regions in our galaxy, to even cosmic distances. So some of the very most distant galaxies are very strongly star formation. And they also produce H2 regions that we then try to analyze, in particular things like star formation rates. And then we have the problem of the powering of the diffuse warm ionized medium. We see that we have one in our own galaxy. We see that we have a diffuse warm ionized medium in all the other galaxies that are forming stars, but we don't quite understand the relationship between the star formation and the powering of the diffuse ionized medium. I mean, we think it pretty much has to be from massive stars, but the details of this and the actual physics of this are still not very well determined. And then in the very early days of the universe, we think that star formation was responsible for the reionization of the universe itself. And so again, this comes from ionizing photons, we think, from massive stars. Again, not completely, well established, because there's the possibility of this also coming from accretion processes. But I think for the most part, people believe that star formation is responsible for a lot of the cosmic reionization. So this is a problem that bears all the way from the closest scales to us here, the sun and its local interstellar cloud, to the very largest cosmic scales of the universe itself. So here in our own area, we have our galaxy, and the sun is in the Milky Way, and we see that we have a diffuse, warm, ionized medium. And as I mentioned, we think that this is pretty much ionized by massive stars. We see that in most galaxies, here's another galaxy just as an example, in most galaxies, the WIM occupies about 60% of the total H-alpha luminosity. And that seems to be completely independent of the star formation properties, the morphology of the star formation rates, the star formation intensities, and so forth, which seems quite counterintuitive. I think this underscores that we don't really understand the relationship between the WIM and the star formation properties of galaxies. There is one notable exception, and that is that we reported in 2007 that starburst galaxies seem to show much lower diffuse fraction of the WIM than we see in other star-forming galaxies. But that is the only exception. And again, I think that underscores that we don't really understand the relationship between star formation and the diffuse WIM. Well, for a while, we had this nice picture where we believed the evidence showed that the WIM was 50% ionized by field stars and 50% by leaking nebulae, meaning that ordinary H2 regions are generally optically thin enough to provide 50% of the ionizing radiation for the WIM. But how did we come to that conclusion? Well, much of that was based on the predicted ionizing photon emission rates, Q, which we get from stellar atmosphere models. And these are not necessarily that well determined. So in 2008, we had done some work with Erica Voges here, which was a repeat of work we'd done back in 2007 to try to evaluate what the ionizing photon emission rates from these massive stars really are. And what we had done back then was take 14 H2 regions in the Large Magellanic Cloud, and we looked at these stellar spectra that were in these H2 regions, so the OB associations that are actually ionizing these H2 regions. And then we took the spectral types and tried to associate them with known, with predicted ionizing photon emission rates from various different stellar atmospheres. And what we found was that on the whole, there did seem to be enough ionizing radiation escaping from these H2 regions just by comparing the H2 region luminosity that you observe with the one that's predicted, that we could account for 50% of the WIM ionization. That was in 1997. Well, the stellar atmosphere models continue to evolve. So it's a very complicated process, of course, trying to model the radiation transfer through the stellar winds and so forth. And a lot of people have been working on this. And what we found was that more recently, that actually the stellar ionizing photon emission rates, the Q values here, have gone down. So what I'm showing here with these green lines, the colored lines, the green and the red lines here, are more recent stellar atmosphere models from Martins et al. And Smith, Norris, and Crowther here as well. These are more recent than the ones that we'd used before. And these are still fairly current right now. And these are all individual H2 regions in the Large Magellanic Clouds. They're the same 14 objects that we had studied back in 1997. And now we're just adding up again the predicted Q values for all of these individual associations. And you can see that the colored lines are much lower than the black lines. The black lines represent the models normalized to the Scherer and Decoter models. These are the co-star models. These are models where they have a unified treatment of the stellar evolution together with the stellar atmosphere. They're unique in that respect. These others are all just stellar atmosphere models. But you can see that the black models, which are the ones we used in 1997, are higher in their ionizing photon emission rates than the colored models. So the colored models pretty much are now predicting that, in fact, the stars are not as hot, or at least not producing as much ionizing radiation, and that therefore, as it turns out, the H2 regions seem to be predicted to be fairly optically thick now, that we can accommodate all of the observed H2 region luminosity with the predicted H2 region luminosity. So what does that mean for the WIM? It seems to cause some problems. Well, if we look at some other studies of the WIM, there are different ways to try to evaluate this problem of the optical depth, and most of them seem to suggest, indeed, that the optical depth is low, that indeed massive stars are ionizing the WIM, and most of these photons probably come from H2 regions ultimately. Here, for example, is some work by Seon in 2009, and this is just a more advanced application of a method introduced by Furita et al. In 2002, where they're looking at the surface brightness distribution in H alpha. These are just for all the pixels in this galaxy. This is M51 in their particular example. And they are just modeling the radiation transfer of the Lyman continuum, including scattering in this particular example. So what they find here is that for low values of the opacity, kappa, and that corresponds to the low optical depth, tau, of course, that they are able to match quite well the H alpha surface brightness distribution that you see in this galaxy, and that includes, of course, all the WIM as well. If you start moving to higher values of the opacity, as in these models on the right-hand side, you can see that the distribution does not match nearly as well. So that's one example where we see that the optical depths that are implied for the WIM are actually quite low. And then spectroscopic studies of the WIM also seem to suggest that there are low optical depths there. So the other kinds of studies, which are somewhat more circumstantial, nevertheless, all seem to suggest that the WIM does seem to have fairly low optical depth. So can we actually take a look at the ionizing photon emission rates from these stars in more detail? Well, my student Jordan Zastro is just finishing her thesis, and one of her projects is to actually take the observed H2 region spectra that you see from single star H2 regions. You can see these are beautiful Stromgren spheres here. So they are ionized by only one star. And then to compare that spectrum of the H2 region with the photoionized model based on various different stellar atmosphere models for that star. So she has a range of different stellar spectral types from O5.5 to B1, so pretty much covering the entire O star range. And she's testing models from 3 different groups, the co-star atmosphere models that I alluded to before, WM basic, which is one of the most widely used, that includes full radiation transfer for the opacities of many, many different elements in the stellar atmospheres, and the T-Lusty models, which are similar but are plain parallel models from Luntz and Hubany. So she uses individual stellar atmosphere models to try to model the H2 region using cloudy for these individual objects. And so she can do things like this, looking at an individual emission line. This is helium-1 5876. It's a recombination line. It's very straightforward. So this is a direct probe of the stellar atmosphere. And you can see that this is her ratio of predicted to observed intensities that you see for the helium-1 line across the different spectral types here. So this is just spectral type on the x-axis here. So all the different stars. Every point here corresponds to a different star, but all of these different colored points correspond to the different atmosphere models. So the blue points, for example, are the WM basic model. The green points are T-Lusty models, and so forth. And for the most part, you can see that she gets a very good agreement between the observations and the predictions for the helium-1 recombination line. So that's very reassuring. And if you take a look here at one example of the SEDs, these are the model SEDs from the different groups here for the best fitting star to an 085 star in her sample here. You can see, indeed, they all pretty much agree with each other down at these lower energies. And the ionization potential for helium-1 is 24 eV. So we see that at 24 eV, that indeed they all agree quite nicely with each other there. And if we look at some other lines, here is oxygen-3, 5007. This gets a little bit more complicated because it's not a simple recombination line, but nonetheless, you can still probe this because you need to have the doubly ionized oxygen now, which has an ionization potential of 35 eV. And for the most part, again, she's getting a very good agreement. These red lines correspond to plus or minus 10%, and that's even smaller actually than our observational errors. I think in the paper we actually made these lines at 20%, which is a more realistic observational error. But she's doing very, very well here with these. you do see that at the later spectral types, we start to have a little bit more of an issue. And we saw that previously also here, that actually the B0 star starts to diverge a little bit between the models. So with the slightly cooler stars, the early B-type stars, the atmosphere models are not as well constrained. Now, if we go to higher energies, we see that we really start running into problems. This is neon 3, 3869, which is ionized at an ionization potential of 41 eV. And here you see a very great dispersion between the predictions for the models and also with the observations. So you can see that this is not doing very well. And then when you look at for example, this one star's variety of models, that at 41 eV, indeed, that's where things really start diverging here. So at the highest energies, there are definitely some problems. And you can see the co-star model, which is the crudest. It doesn't have the highest resolution. It's the most approximate. You really have a strong overestimate there in the continuum. And when you go here for an 08 star, that indeed the co-star model is so high that it's way off the plot here. I think this is maybe its error bar, but it's not even on this plot. So indeed, it's strongly over-predicted by these models. Another thing you can see is that there are systematics between these different stellar atmosphere codes. So for example, here you see that the green points, which are T-lusty models, are systematically under-predicting for the high ionization species. And co-star, as we just mentioned, systematically over-predicts across all spectral types. And you could see that again here, maybe not quite here, but maybe in the next one. So this is 3727. This is a low ionization species. And here you can see that for the low ionization species, T-lusty systematically over-predicts because the atmosphere for T-lusty is softer. So it will be stronger in the lower ionization species, whereas the co-star models with the red stars are the ones that are under-predicted the most. So you can see how we can really compare the different models, the different families of models with each other here. One other thing that she's finding, of course, we've implied here that the blue squares and the triangles are doing much better. Those are based on the WM basic code of Paul-Drach et al. So we're concluding that for now does seem to be working the best. And one of the other things that she can do here is to look at the spectral type to effective temperature relation that we get from this kind of analysis. So normally, when people create a spectral type to effective temperature relation, they are trying to make a calibration. They take the atmosphere of a star and they do a very careful modeling of the actual photosphere of the star where they match the lines exactly. And then they say, okay, well, this is an observed star and here we have our model, so this temperature must correspond to an 08 star or whatever. Here we can do this actually with a nebula. So we have from the nebula the implied effective temperature that is ionizing the nebula, and then we can plot that against the spectral type of the star that's actually observed. Now, we don't have very many points, and as you can see, our data have very large error bars on them. So I wouldn't try to use what we have here as an actual calibration, but you can see that with a lot more points and a lot more accurate data, that in fact we may be able to move towards some kind of spectral type to effective temperature calibration that's based on the nebula. And I think that would make a very, very interesting comparison with what you do with a normal spectral type to effective temperature calibration that's based on the photospheres of the stars. Again, you see that we have more trouble here with the late type stars, the B stars, but in general our points are falling in the right vicinity. We see that these lines are the ones that are real calibrations from the literature, and our results are generally in the same area. Okay, so back to our original question of whether individual H2 regions are optically thin. So this is some work that I've done with my former postdoc, Eric Pellegrini, and we decided to try to see if we could do this more or less directly, answer this question directly. And so we're taking what is not a new method, but fairly old method, but actually trying to develop this more. And we're calling this ionization-parameter mapping so that we can try to look at the actual ionization structure of the nebula. So here we see some examples. These are data from the Magellanic Cloud Emission Line Survey. This was carried out by Chris Smith using the University of Michigan Curtis Schmidt telescope at CTIO. It's a complete emission line survey of both Magellanic Clouds in H alpha, O3, and sulfur 2. And these images that I'm showing you are from the SMC, just a couple objects, and they are ratio maps now of sulfur 3 to O3. And so we're plotting these so that sulfur 2 shows up as bright, so it will be white, and then the O3 will show up as dark here. And so what you're looking at with these H2 regions is kind of what you saw just a moment ago in color. These are just Stromgren spheres. You see that the high ionization region is near the center because it's nearest to the ionizing source. So the ionizing source is in the center. We have the high ionization species in the middle. And then if these are Stromgren spheres, they're optically thick. And so when we move toward the edge, you will transition from high ionization to low ionization. So you should see an envelope around the high ionization species, and that would be a low ionization species. So for example, sulfur 2. So the white sulfur 2 is making a very nice envelope around the black O3 here. And that shows you that you have the ionization structure going from high to low as you would in an ordinary Stromgren sphere. Now, contrast that with this object right here, which is actually the same as this object. And you see that you don't have that effect, right? Instead, you are seeing that this looks black all the way through. You don't see any evidence of the lower ionization envelope around this object the way that you do for these objects. So this object must be optically thin. It is allowing ionizing radiation to escape out of this object, and it's available, therefore, to ionize the interstellar medium. And you can also see that in examples like this. These are blister H2 regions where you are optically thick on one side and optically thin on the other side. And we have two beautiful examples right there. So going back to this one, the other thing that you notice here is the morphology, right? For the optically thick ones, we see that they are round. They are Stromgren spheres. And so this object is not round. It's not a sphere. And furthermore, that's also consistent with the radiation hydrodynamic simulations from Arthur et al., where they show that objects that become optically thin and are essentially ionized with very strong ionization fields develop these kinds of instabilities. And so they look very morphologically disrupted with champagne flows and all kinds of interesting morphology here in the object. So things that are round and look like Stromgren spheres probably are Stromgren spheres, essentially. So this looks very, very simple. Of course, I do want to add some caution to this, that things are never as simple as they seem, but nonetheless, I'm obviously arguing that this works pretty well. Eric Pellegrini ran a number of cloudy models here of the H2 regions. Here's the ionization structure for a cool star's H2 region on the left and a hot star's H2 region on the right. And for example, the black line here is the ionized hydrogen. And then let's take a look at these different species. He has plotted different ionization stages for oxygen and for sulfur. And we had plotted O3, which is doubly ionized oxygen. So that's the solid line here, the solid blue line. And we had plotted singly ionized sulfur. So that's this dotted line right here. So S2 and O3 here. And if you see the low ionization envelope around here, then you're looking at this region, right? This is the sulfur 2 dominated area over here. And if you see that, then you're pretty close to an optically thick region, a tau of 1. Supposing you truncate your nebula here instead, that means you're density bounded, and it means that you have a low optical depth of, say, 0.3 here, and you're completely dominated by the O3 region. You don't see the sulfur 2 region, which is over here, or at least you don't see it as an envelope around the object, right? Now let's look at the cooler star's nebula. It's obviously very similar in structure, but if we take a look, let's say, for example, here, supposing the object is truncated here, we still see that we have a region that's dominated on the outside by the low ionization species, by sulfur 2, right? And yet, we're looking at a tau of 0.5. So tau of 0.5 corresponds to about 60% of your ionizing radiation escaping still. So you can actually be quite optically thin even if you do see the envelopes, just as a caution. And this applies mainly to the lower mass stars, to the cooler stars. So what I can say definitively is that you do have some clear limits here. If you don't see the transition zone, then you're definitely optically thin. If you do see the transition zone, then you are probably optically thick. That's if you have two different species that are probing the ionization structure. If you have three species, then things are different, right? If you have three species, you can really constrain what's going on there, and you can pretty much directly measure what the optical depth of the object is. And so that's something that we are very excited to try. We have obtained some data for three species now, including oxygen-2, for M33. So that's something that we are going to be starting soon. Okay, so let's see how well this actually works. We have those 14 H2 regions that I talked about earlier where we know what the ionizing stars are. And that means that we can make pretty much a direct estimate of what the escape fraction of the ionizing radiation is in those stars, in those H2 regions. So that's what we calculated for those objects here on the y-axis. So these are the sort of more or less measured values of the escape fraction based on the H-alpha luminosity and the predicted fluxes of the observed stars. And then we just use this ionization parameter method to just categorize whether these objects are optically thick, optically thin, or blister objects. So just three different categories here. And we just said crudely, if the object looks optically thick, just from its morphological ionization structure from the ratio map, if it looks optically thick, let's assign it an escape fraction of 0, just to be simple. If it's optically thin, let's assign it an escape fraction of 0.6, which corresponds to tau of a half. Again, just to be really simple. And if it's a blister object, meaning only half of it is optically thick, then or less, or whatever, then we give it exactly half of the value for the optically thin escape fraction. So that's what's plotted on the x-axis. So this is extremely crude, as you saw. Very, very crude. And yet we get a very nice correlation here. The objects are shown with different color points. The blue ones are points for which we have spectral types of all the stars. The green points are objects for which we have spectral types of some of the stars, and the rest are inferred from photometry. But basically, you can see that they all fall on this correlation quite nicely, meaning not really correlation, but a one-to-one correspondence, right? Because this is a quote-unquote measured value, again, with the caveat that the ionizing fluxes are not that well determined for stars. This looks kind of scattery, but the actual dispersion on this relation is only 25%. So even with this extremely crude way of just categorizing the objects as optically thick, optically thin, or blister, we're already seeing that this seems to work pretty well. Now, for any individual object, of course, you don't necessarily know what's happening. But if we were going to look at a whole collection of objects, an entire population of H2 regions, then, in fact, I think we can try to determine some important properties of the H2 region population. And that's what we will move toward. Now, before talking more about that, I want to also mention that this method, ionization parameter mapping, will work in the line of sight as well. So this here is a profile across an optically thick object. This is a Stromgren sphere. You can see the sulfur-2 using the axis on the left, and oxygen-3 using the axis on the right here. And you can see that it shows the envelope of sulfur-2 on the outside very nicely. Also, in the line of sight, which is right down the middle of this nebula, you see a minimum sulfur-2 level of sulfur-2 to H-alpha of about 5%. So if you imagine looking at the object, then looking through the line of sight, you should still get that envelope of the low ionization species. So you still see it, even though you're not looking at the edges of the object. So you should see some minimum value, indeed, even in the middle of the object for the low ionization species. And for the Magellanic Clouds, for the LMC anyway, it's around 5%, and this will depend on metallicity somewhat. This object, in contrast, shows a sulfur 2 to H alpha value of 0 in the middle, right? So the contrast between these two objects is quite noticeable. So here you see something that does have an envelope at least on one side of the object. It's a sort of blister thing. But in the middle, looking right down the middle where you strong O3 emission, you also see 0 sulfur 2 emission. So this object is optically thin in the line of sight. So it's a very nice method. You can use it to determine roughly whether an object is optically thick or optically thin just by looking at the object and also by looking at the sulfur 2 emission that's in the line of sight as well. So we decided to do this across all the objects in the Magellanic Clouds, just as a population, again, because for any individual object, we can't be too certain about what's happening. But as a population, we can gain some interesting information. This is how it works. This is just a generic region of star formation in the LMC. And you can immediately see, this is again sulfur 2 to O3 ratio, that there are some Stromgren spheres very clearly notable in this image right here. And then there are also some other regions that are very clearly optically thin. So that's how it works. And you can look at the entire galaxy. This is a bit more difficult to look at because it's such a wide-angle view. But you can get a general impression here that some regions in the LMC are optically thick and other regions are quite optically thin. And so we did this for all the objects. And by the way, here, the background noise is really quite high because for the M-cell survey, the narrowband images have not been continuum subtracted by the M-cells team, whereas for the SMC, they have. So the SMC has a much higher signal-to-noise ratio map than the LMC, and here you can immediately see all the background emission as well. That comes from the WIM, the diffuse warm ionized medium. So you can see all of this white background emission here. And we know that the WIM is dominated by lower ionization species like sulfur 2 and nitrogen 2. So you can see it coming out very clearly here. And even though you have this background of white, of the low ionization sulfur 2, that nonetheless you can clearly see the H2 regions that are optically thick against that background. So you don't really have a confusion problem there. And that's because the H2 regions tend to be higher density objects, and so they have good signal to noise against the diffuse background. So here is a color image where the green corresponds to the neutral hydrogen column density, and then red now corresponds to strong sulfur 2 to O3, blue corresponds to strong O3 to H alpha. So the objects that are strongly optically thin would tend to appear more in blue, and the objects that are optically thick should have the envelopes in red. So one thing that you see here is that the brightest H2 region in the SMC, which is N66, actually is buried in the middle of everything. It's surrounded by a lot of this red emission, which is this low ionization species, and the green, which is the neutral hydrogen. So that very bright H2 region is probably optically thick. And in contrast, this much less well-known region out here, DEM167, which is on the edge of the galaxy, looks like a very strong candidate for allowing ionizing radiation to actually escape from this galaxy. So we see that the location of the H2 regions and their luminosity are very important in determining whether you may actually have escaping radiation from an entire galaxy. I'm not saying that we actually have radiation escaping from here, but you can see that this is far more likely to cause that than this right here. And that's consistent with models of galaxy evolution that have been done by Knedin et al. So here's the region in the southwest corner of the SMC, and this is the neutral hydrogen column density map. And over here we see the ratio map again. This is reversed now, so that black corresponds to sulfur 2, strong sulfur 2. And you can see this whole thing must be optically thick because you see the ring of sulfur 2 around the O3. And that's completely consistent with the neutral hydrogen distribution that you see here. So we were very interested in comparing and contrasting the H2 region optical depth properties with the neutral hydrogen properties of these two galaxies, because the LMC and the SMC are very different in their gas properties. You can see that from these column density maps. So the LMC is pretty much a face-on disky galaxy whose H1 is very filamentary and very pockmarked due to feedback and so forth, whereas the SMC is much more amorphous, much more three-dimensional. So the properties of the H1 in these two galaxies is really quite different. These are on roughly the same scale. I've plotted these. And these galaxies are at very much the same distance. These surveys were taken with the same telescope. So the contrast that you see between these two is real. So let's take a look at how the neutral hydrogen properties relate to the optical depth of the H2 regions. So just from ionization parameter mapping, we again categorize the H2 regions as optically thick, optically thin, or blister. If they're blisters, we counted them as optically thin. So optically thick and optically thin. And what we're looking at here is the frequency of the optically thick objects as a function of hydrogen column density. And you can see that there's a very nice correlation, as you would expect, that as you go up in hydrogen column density, you end up with more and more optically thick objects. So that is reasonable. One would expect that to be the case. And you see that in both galaxies. And one thing that's also worth noting is that for the lowest column densities, we do see that the optically thin objects actually dominate. And again, this is the case in both galaxies. So what is notable is that even though the properties of the neutral hydrogen are so different between these two galaxies, that in fact, we see that when their quantitative behavior with the optical depth is actually very similar to each other. Now you see the x-axis is different, and that's because the LMC is pretty much face-on, and then as I mentioned, the SMC is more three-dimensional. So these are higher columns, but they are in fact quantitatively, other than that, quite consistent with each other, as you can see. Here are the distributions in the hydrogen column densities in the line of sight of these H2 regions. And you can see they're actually quite similar to each other between the optically thick and optically thin objects. And the LMC is plotted in blue, the SMC in red. The thick line, as before, corresponds to optically thick objects, and the thin line corresponds to optically thin objects. But you can see that although the distributions are similar, that in fact the optically thick objects tend toward higher column densities than the lower objects. So the distribution favors the optically thick objects, and they do it in both galaxies, once again, the LMC and the SMC. We can do the same thing with the H-alpha luminosities. So here are the distributions of the H-alpha luminosities of the H2 regions in both galaxies. Again, as before, SMC in red, LMC in blue. And the optically thick objects now show a much stronger peak toward lower luminosities than the optically thin objects. So here's the optically thin objects for the LMC, and you can see they peak at much higher luminosities than the optically thick objects. Same thing in the SMC. The optically thick objects are peaking at lower luminosities than the optically thin objects over here. And so if we run the same correlation that we did a moment ago, for the luminosities, here we see the frequency of optically thin objects in the LMC as a function of H-alpha luminosity. And we can see that there's a very strong correlation such that the frequency of the optically thin objects is very strongly correlated with the H-alpha luminosity, and of course inversely for the optically thick objects. And we see this in both galaxies. So this is the LMC here, and then the SMC over here. The SMC has many fewer objects, so the noise is going to be a lot higher in the SMC, but you can see that these two plots behave very similarly to each other. And this actually confirms an idea that was suggested by John Beckman back in 2000 and his collaborators, that in fact the most luminous H2 regions are going to tend to be optically thin. And he turned out to be exactly right about that, except that the crossover luminosity where that happens occurs at a much lower luminosity than they had predicted. They had suggested something like 10 to the 38.6 ergs per second. Here we actually see that the value is 10 to the 37 ergs per second at which the optically thin objects dominate. And interestingly, once again, the same value is seen in both galaxies, 10 to the 37 ergs per second, in spite of the very different H1 properties of those two galaxies. So in fact, 10 to the 37 ergs per second is a very low luminosity. It's sort of like the Orion Nebula. So what that's telling you is that when you look at an H-alpha image of a galaxy, you see all of these bright H2 regions. Most of those bright H2 regions are going to be optically thin, as a matter of fact. But not all of them. I mean, the other thing to take note is that even at very high luminosities, you find optically thick objects as well. So very important to keep in mind. So that means that, in fact, if this is correct, that we do have a lot of ionizing photons available to escape into the interstellar medium and to ionize the WIM. And in both of these galaxies, we have about 40% and 33% in the LMC and SMC, respectively, of the H2 regions being optically thin. Overall, for the entire population of H2 regions, we see that the escape fraction is about 40% in these galaxies. And that means that we could try to make some estimate of how many ionizing photons are actually escaping out of the entire galaxy, if they are, and that would be 4% and 11% in the LMC and SMC, respectively. However, that has a very large error bar on it. I would say something like 10 to 20% for the error bar. So this is also consistent with there being zero escape fraction from the Magellanic Clouds. But it is interesting that we could account for some within the error bars as well. So I think we've already demonstrated that this method is actually quite useful, quite simple, and quite powerful. What about starbursts? Can we scale up this whole problem to looking at starburst galaxies? We know that local starbursts have tended not to show very much high escape fractions at all. In fact, in local starbursts, we never see any ionizing radiation escaping from them, either by direct observation or by inference from absorption line studies. They always appear to be completely optically thick. And more distant galaxies, we actually see that there are a few detections where the Lyman continuum has been seen, but in general, again, this is something where we find surprisingly low fractions of the escape fraction that we see from even in those distant Lyman break galaxies. This right here is a plot from Grimes et al. These are fused spectra of local starburst galaxies. And what we are seeing here is that the Lyman continuum does not appear in any of these galaxies, and that would be to the left of these arrows here. You can see the continuum is completely flat, so there's no detection whatsoever of the Lyman continuum, and that's very typical of observations that we see for local starbursts. So on the other hand, we would expect local starbursts to show some kind of escape fractions, and especially more distant ones. And so could it be that somehow we're just not actually detecting them? So could we actually apply this technique of ionization parameter mapping to entire galaxies? So that's what we're trying to do here, where we are applying this to starburst galaxies. And we are using the Maryland-Magellan tunable filter at Magellan, obviously. This is another project done by my student, Jordan Zastro. And what we're showing here is narrowband image of sulfur-3 in red, red continuum in green, and then sulfur-2 in blue. So red is the high ionization species. And you can see in this composite that very nicely she is actually detecting an ionization cone in this galaxy, NGC 5253. NGC 5253 is a very well-studied galaxy that is right in our backyard. So it's a bit surprising that no one has ever identified something like this in this galaxy before. So I think this, again, shows how well this technique works. And if we take a look at the ratio map here, this is sulfur-3 to sulfur-2. Sulfur-3 is black, sulfur-2 is white, and here is the ionization cone once again. And so she's continuing to work on a sample of some more starburst galaxies that are nearby for the rest of her thesis, which hopefully she'll be finished with that this summer. And it suggests that because we see this ionization cone extending out in some random direction outward, that the reason why we don't see direct evidence of the Lyman continuum in galaxies, and why we don't see any evidence of any low optical depths in such galaxies, might be simply an orientation effect, that the line of sight to this narrow ionization cone is not pointed toward us. And so that's why these galaxies appear to be optically thick, when in fact there's a possibility that they might have pretty significant escape fractions. So that is a very tantalizing result that we have. And we also wanted to take a look at some galaxies that we thought might have the highest likelihood of actually being optically thin in the local universe. So it has recently been reported that there are these extremely high ionization galaxies called the green Pea Galaxies because they look very, very green and they're unresolved in the SDSS survey, which is how they were discovered. And the greenness comes from the extraordinary strength of oxygen-3, 5007. So my student, Ann Jascott, is working on this. She's actually just gotten this paper accepted by APJ. And so we thought, can we actually see whether through some emission lines ratios we can really try to establish whether these objects are optically thin or optically thick. So here is the BPT diagram, the Baldwin-Phillips-Turlovich diagram. Oxygen-3 on the y-axis, nitrogen-2 on the x-axis. And here is a large subsample of green peas that Anne has selected. And these are some of the high ionization ones that she's especially focusing on are these diamonds right here. So those are the very highest ones that she has chosen to look at. And I think these were just selected on perhaps the very, very strongest values of O3 and the fact that most of these are also helium-2 emitters. Right here, this line is what you could consider to be sort of a boundary. It's a model that was run by Cooley et al. For a very high excitation track for the photoionization due to ordinary star formation. In other words, thermal ionization source right here. So that represents a sort of high ionization limit. And you can see that these objects are all following this track very nicely. They're not over it, of course, because this track represents a bit of a limit, as I mentioned. But they're all very clearly on the photoionization path that is caused by a thermal source. So these are clearly not ionized by AGN. The AGN, as you know, are up in this region right here. And this clearly shows that these green peas are not ionized by AGN. They are helium-2 emitters, especially these extreme objects that are ionized by the diamonds. And so Anne identified that as being the real criterion that we need to try to identify what it could be ionizing these sources. And can we actually explain the ionization, the very high levels of excitation of these objects by simply optically thick ionization, or could we actually infer that some of these might be optically thin? So the idea is if you have very strong high ionization species and very low ionization species, as I mentioned earlier, that could imply an optically thin scenario. So that was kind of our thinking behind that. So there are a few different possibilities. This is just the same list that I had on the previous slide. Wolf-Rayet stars are, of course, the first thing that you might think of. And so we'll take a closer look at that. Anne has run a whole bunch of photoionization models with Wolf-Rayet ionization sources. Another possible stellar source would be very hot metal-poor O stars. So the Geneva group has not too long ago suggested that if you have low metallicity stars and that these stars are rotating and that they have very good internal mixing, that in fact they may evolve at much higher metallicity than has previously been suggested. And you may get effective temperatures of up to 60,000 degrees or something like that. So, you know, that's a possibility, but I would say, first of all, that most of these green peas are around 0.2 solar metallicity. So they're not super metal poor. And secondly, no one has ever seen such a star. And we do have plenty of H2 regions at these kinds of metallicities in the local universe, but we don't see any evidence for, you know, these stars being those temperatures, because you don't see these H2 regions with such high excitations from individual stars or even OB associations. So there's no real observational evidence yet that such stars actually exist. And so I consider that to be really pretty speculative right now. And I wouldn't really want to suggest that based on Occam's razor right now. AGN, you saw, were already ruled out just by their position on the BPT diagram. And then there's the possibility of high mass X-ray binaries. So if you have high mass X-ray binaries, you must have a lot of them. And the system must be aged enough so that you have the black holes that are the high mass X-ray binaries. And so Anne can calculate the burst mass that you get in these starbursts. And she's basically come to the conclusion that you don't get enough of them, enough high mass X-ray binaries given these burst masses by at least an order of magnitude. So the high mass X-ray binaries just simply aren't, you don't get enough of them to explain the high ionization of these objects. Furthermore, there's this criterion here offered by helium-13819. If you see this emission line, it's been suggested in the literature that that implies a very, very young starburst, something that's only 2 million years or so in age. And 2 out of the 6 galaxies actually show that line. So that suggests that these are, in fact, extremely young starbursts, which again would not be consistent with the high mass X-ray binary scenario. This also causes the Wolf-Rayet star scenario to be a bit problematic as well, as you can see. Then there is the issue of shocks. So shocks might be another way to get helium-2 emission, and we'll take a look at that as well. So here are some photoionization models that Anne has run using Wolf-Rayet stars as the ionizing sources. Here's helium-2 4686 on the y-axis relative to O3 to O2, which measures the ionization parameter in oxygen on the x-axis. Red are WN stars, green are WC stars, and blue are ordinary O stars. You can see that ordinary O stars will not work. The data points are right here. And you can see they're right on the uncomfortable edge of these models right here. So very high ionization parameter. We need to kind of scoot the ionization parameter to even higher values. This right here assumes a density of 100 atoms per cubic centimeter. Both the WN and WC models will work. If she causes this to be run with a 1,000 atom per cubic centimeter density, that will increase the ionization parameter, and she can get them in there. That's a very, very high density for these starbursts. It's a bit uncomfortably high. She does have some sulfur-2 observations, but they haven't been very good at yielding actual densities. So this still remains possible. It's, as I say, it's a little uncomfortable, but it remains possible. What is not really possible is the WC stars, because they have very broad emission lines that are easily spotted, and we don't see those in these spectra to the necessary limits. So if they are Wolf-Rayet stars, they must be early WN stars. Here are some more photoionization models. These are a little bit busy, so we'll just take them step by step. This plot in the upper left is the same as the one I just showed you, helium-2 4686 versus O3 to O2. Now we're looking at ionizing this with an entire starburst population. So these are plotted for different ages, 0 million years here, and then 3 million years is just below the plot, 4 million years, and 5 million years. What's happening here is that as the stellar population ages from 0 million years, the helium-2 emission will go down because the ionizing stars are expiring. But when the Wolf-Rayet stars come in, it will suddenly go up. So that's what's happening here at 4 million years. And then again, as the population continues to age, then the Wolf-Rayet stars also expire and it goes down again. And then these lines, as you move to the right, correspond to more and more density-bounded scenarios. So the optically thick model is the leftmost line on each of these models. And then as you move to more optically thin scenarios, you're moving in that direction. So the objects are fairly consistent with being optically thick at ages between 4 and 5 million years, again implying that Wolf-Rayet stars are really the ionizing sources in these particular models. The red and the black are just, again, different ionization parameters, which are specified essentially by the distance of the gas from the ionizing sources. But you can see the black models are really the ones that fit. And those, again, are run at this very, very high density of 1,000 atoms per cubic centimeter. Let's look at a different species. This is neon-3, 3869 on the same x-axis. And you have, again, here different age, 0, 3, 4, and 5 million years. And this looks very similar here. So we are matching the data between 4 and 5 million years, optically thick. Down here, we're looking at the ratio of argon 4 to argon 3 seen in the H2 regions of these objects, or seen in the emission lines of these objects. And then again, 0, 3, 4, and 5 million years, looking quite similar to the other two plots. And here, we're looking at a low ionization species, oxygen 3 versus oxygen 3 to oxygen 2. Sorry, oxygen 2 versus O3 to O2. And here you see that the data actually fall off the plot. So this is not actually working very well right here. And it's tricky. This is one of these instances where we're actually not matching the data very well. Now, we've mentioned that Wolf-Rayet stars are a very plausible ionization source. They must be WNE stars. So let's look for the Wolf-Rayet bump. We actually do not see the Wolf-Rayet bump in these galaxies. This is a stacked spectrum of 15 of the most extreme green Pea galaxies. And you don't see the Wolf-Rayet bump right here, as you would expect to see for the WNE stars. However, this is still allowing within the limits that these Wolf-Rayet stars are actually there. She needs something like a few thousand Wolf-Rayet stars, and the ratio of the Wolf-Rayet emission to the O-star emission is still permitted within this. So she's getting more observations with IMAX at Magellan, and so far she has a few deeper observations of a couple galaxies that again are not showing evidence of the Wolf-Rayet bump to even lower limits. So that's work in progress right now. So now to the question of shocks. So we have not confirmed the Wolf-Rayets, what we can take away there. So shocks have been suggested by a number of people for ionization sources of helium-2 in starbursts, including by Gusieva et al. And others. So if some of the helium-2 is from shocks, we need to subtract that from the emission that we're assuming is due to the H2 regions, to the ionized gas. And so that makes the data move along this arrow to the down and somewhat to the right. So that would move these points in that direction. Over here, we would see that the shocks would move the data to the right. And that would be along the same direction as you see that density bounding goes. And then over here, the shocks could go in either up or down, depending on the velocity of these shocks. And then over here, shocks would move the emission ratios so that you go to the lower right. And that is, again, in the same direction as the density bounding arrow. So what this implies is that if shocks are present, they would actually make it far more likely that the objects are density bounded. So she's really exhaustively looked at all of the possible ionization sources for these objects. And so in summary for these, we essentially are finding that Wolf-Rayet stars are so far consistent with ionizing these objects. We need to have the special age between 4 and 5 million years, dominated by WNE stars, which so far have not been confirmed, but which have not been ruled out either. There is this problem that 2 out of 6 of the galaxies are apparently too young, according to this criterion, but how well does that criterion really work? So it's a little problematic, right? This density that we're using is very high, and we have some things are not quite where we want them to be, but we cannot rule this out. So that remains a possibility. These we've ruled out. Shocks are very plausible source of helium-2 emission, and if they are present, then that will strongly increase the likelihood that these objects are optically thin. Okay, so I think these kind of show that there is a very plausible likelihood that these objects are optically thin, but they could very well still be optically thick and ionized by WNE stars with some caveats and problems. Okay, so to summarize, we've used the single star nebulae to evaluate the stellar atmosphere models, finding that WM basic so far is working the best. We are seeing a lot of uncertainty in all of the models above energies of about 40 eV in the SEDs, and that, interestingly, we may someday be able to move toward a radiation-based spectral type to effective temperature relation, which can be compared to the photospheric ones. We have developed ionization-parameter mapping, which we've applied directly to the Magellanic Clouds. I think I've shown that this is a very powerful and elegant technique, and finding that about 37% of the objects are optically thin in both galaxies, and that we see a strong correlation with the optically thick objects with the hydrogen column density and the optically thin objects with the H alpha luminosity, such that the optically thin objects dominate above luminosities of about 10 to the 37 ergs per second in H alpha. We've also applied this method to starburst galaxies, finding that in NGC 5253, there's an ionization cone suggesting that this galaxy actually has a significant escape fraction, and that the reason why we don't see escaping ionizing radiation from many, many starbursts may simply be due to an orientation effect. And that looking at the green Pea Galaxies, which are some of the most extreme and hottest starbursts in the local universe, that these objects may be ionized by WNE stars, but that there are still some problems with that model, and that if shocks are present, as we would expect in these objects, and if those shocks are contributing a significant fraction of the helium-2 emission seen in these galaxies, that they may actually imply that they are, in fact, optically thin. Thank you very much.
Thank you very much for this nice talk. We have time for a couple of questions.
A very nice talk. About the Greenpeace galaxies, there is something that troubles me in the sense that you are assuming that you have an instantaneous burst of star formation there, but you have a galaxy. I think that is very, well, I like starbursts, I like instantaneous bursts. It's the most easy thing, but it's very difficult to maintain an instantaneous burst in a big size galaxy. So maybe it's better to assume that there is some continuous star formation there that has been not considered by you. All the issues that you are talking about, the ages, high mass exuberance goes down because you haven't any particular age. You have a very large range of age, and you can play more. And I think that physically is more consistent, not only an instantaneous burst. I know that it's more easy. And in the same way, you are thinking about this starburst galaxy like a single H2 region. And it's very difficult to have, well, I have done this kind of models. But actually a galaxy is not a H2 region, but a summary of lot of H2 regions with different dates and all these things. So it's again that the issue of include sun star formation, history there, and include how different H2 regions behavior and what is the mixing of this H2 region to make this plot and to then, well, it's just one idea.
Yes, I mean, I completely agree with you. I think it's more plausible if you also include continuous star formation. Anne has actually run the continuous star formation models as well, and it turns out that they don't work. And I believe that's because you continue to form more O stars all the time. And so if you want to maximize the Wolf-Rayet emission to the O stars, then you have to look at a single burst, essentially.
Yes, but I do know the issue is not to use a continuous star formation model and put it in a photon ionization model, but to compute several H2 regions and make the sum of these several H2 regions.
Yes, yes, yes.
And this doesn't work. All these diagrams would change a lot.
Right. I know that we talked about that also when we were doing this project, and I think you essentially get it's the same problem in the sense that, especially if you assume a luminosity function for the H2 regions, right? Then you end up with a lot more lower luminosity H2 regions that have cooler stars, essentially. I mean, you're going to reduce the number of Wolf-Rayet stars, or the ratio of Wolf-Rayet to O stars when you do that. And I think that's, she's trying to maximize the number of Wolf-Rayet stars so that we can account for most of the ionizing luminosity. And so if you start adding in more lower mass stars, then you reduce the ratio of Wolf-Rayet to O stars. Otherwise, I agree with you, and that was why we tried that also.
The result you are showing has a lot of implications, not only the interpretation of the warm interstellar medium, which is important, but many more. In particular, if a nebula is optically thick, can we use the BPT diagram? Second question. I have three questions, but they have to do with it's so important, your result, that if confirmed, they would make us to reconsider a large number of things, a large number of tools, and also the diagnosis of many things, including emission lines,
Thank
profiles.
you. Would you serve on the proposal review committee?
So this is very important. But because of that, first, can we use the BPT diagram? Second, a technical thing. You are using a map for the ionization map for the galaxies 52, 53, using tunable filters, which, as you know, to have a very precise photometry of tunable filters beyond the monochromatic area is quite tough, and therefore the uncertainties can be very high. And then the third question is, what would you expect of more simple things like, for instance, local compact H2 regions?
Okay, three questions. So the first one was the BPT diagram. So that's right here. And so if, in fact, we have an optically thin scenario, I think we simply need to shift what we're looking at slightly. So that means that the nitrogen 2 would tend to be, would be too low if we have an optically thin scenario. So that means that the objects should move more toward the left on the BPT diagram, whereas oxygen 3 would still, oxygen 3 would remain unaffected, essentially. So I think we can use the BPT diagram because it would still, these things are moving to the lower left. They're not moving into the AGN contamination region. But yes, they're not going to fall in exactly the same region. Another diagnostic that I think we really need to be careful about is the star formation rate. It's simply that, right? Because we use H-alpha luminosities to measure the star formation rate. And if those H-alpha luminosities, in fact, are underestimated significantly, then that will affect star formation rate estimates as well. But yes, clearly these objects will shift from where they are on the BPT diagram. And it depends on how strongly optically thin the objects are. And in general, things are never completely optically thin because otherwise we would have known it by now. Okay, so your second question was about, the maps, right. Yes. So I just learned yesterday that the tunable filter on OSIRIS is, basically does not have a very large monochromatic region. Whereas that you actually use the whole thing. Whereas on the MMTF, we only use the monochromatic region. And so hopefully our calibration is okay here. We don't really, whoops, I went in the wrong direction. We don't really worry too much about it if the object falls well within the monochromatic spot. And this object is something like, 3 or 4 arc minutes across, and the monochromatic spot is something like 7 arc minutes across on Magellan. Yeah, the field of view is 15 arc minutes. So yeah, hopefully that's not a problem with this. Whoops, yeah. And the compact H2 regions, so yeah, those tend to be more embedded. So that's a very interesting class of objects. And because they're embedded, I would assume, therefore, that they are most likely optically thick. They're so young that they're still in an optically thick regime, I would imagine. But I haven't looked at them. They would be very interesting to look at. But the fact that they're defined by their compactness and tend to be very strong infrared emitters, right, suggests that they are still deeply embedded and that there's a lot of molecular gas around. But worth looking at.
Okay, Sally, I have a question and a comment. The question is about the escape fraction, which you've calculated to be now about 40% approximately, using from the LMC and SMC, using these gas-based diagnostics. Your original values years ago, using stellar emission spectra and Q values, was about 50%. So there's a difference of only about 10%. Is that consistent with the difference in the outputs of the models that you presented? Is that what you'd expect?
Which models?
Well, you've presented a whole set of models, the older models with more UV emission and the newer models with less UV emission. Is that difference about 10%? Or it seems to me that it might be a lot more. That's the first question. And the comment is about the reason for H2 regions being optically thick or optically thin, which may well have a lot to do with inhomogeneity rather than simple fall off of density as you go outwards. And that would make a tremendous difference to all of these things. I don't want to raise more points here, but I think it's something that has to be taken into account. And finally, I would say that I would rebut the idea that you can't adequately calibrate the series field over the whole field. You've done it quite well.
I didn't mean to say that.
No, you didn't actually say it. But in fact, it's not a big problem. I mean, it's one of these non-problems that people have raised as problems, and it isn't a problem. It's easily resolved.
Okay. So yes, you've just pointed out that I contradicted myself because here we found a result that was similar to what we'd reported in 1997, that the escape fraction from the H2 regions is about 40–50%. Whereas in the earlier plot, we can clearly see that the discrepancy is more than that, more than 10%. So here you can see that, the variation between these colored lines and the black lines is almost 50% itself. So yeah, I mean, those two things don't seem to agree with each other. Either that or our work wasn't as good as we think it is either. So it's funny because it depends on who you talk to. Because, this work, the 2008 paper, when I reported this to some of the stellar people and said, oh, look, now the H2 region luminosities agree with the predicted ionizing fluxes, they said, oh, see, now we've done a really good job and now they're correct. Whereas when you show this to the WIM people, they're like, oh, there must be something wrong with these stellar models. So you can do what you like with this. And then the inhomogeneity, yes, I think you're absolutely right about that. And one way that we are following this up right now, in fact, I've just hired a new student, is to look at the Spitzer data for the LMC and SMC. There's a SAGE survey, and that with that, we are basically repeating this correlation of the optical depth against what we'll see as, for example, dust mass and so forth. And I think that will hopefully help to clarify that. But, without looking at individual objects, and again, with individual objects, it's difficult to know exactly what the optical depth of any individual object is in the first place. So it starts going down a slippery slope. But I think at least with this first step, we may be able to find out something interesting.
Okay, I think we should stop here. Remember, there's now scientific coffee in the library, so let's thank the speaker again.